Hi everyone. Good morning. Hey, how? Um, first and foremost, I would like to thank ICBS for for the invitation, for their incredible hospitality, and this enormous intellectual feast. It's a pleasure and a privilege to be here. Uh, what I wanted to talk about today, it's an area that I am kind of new to, but the theme that led me here is very old. So the theme is, what are patterns of randomness that we see in this deterministic world that we live in? Okay. So my goal for today would be to tell you about one manifestation of such randomness inherent in deterministic structures, which is in the world of normal numbers. Okay, so let's get started. So I'll take a page out of Rupert's book and I will pause for questions. Please interrupt because the whole idea is to get some message across. Okay, so we are going to, so let's say B is always going to be an integer, at least two. Okay, we know that every number x in 0 to 1 and indeed on the real line can be written as in the form x equals summation xj b to the negative j, where j goes from 1 to infinity, where these xj's belong to the set of integers from 0 to b minus 1. Okay, so this is what we already know, and these xj's are called the digits, the b-adic digits of x. We are going to say that x is b normal if the number x is completely fair to all its digits. So, and what does completely fair mean is that it's partial to every specific digit and also to every possible block of digits. So, if every k greater than or equal to 1 and any choice of digit sequence d1 through dk in z mod b to the k, we are going to look at the frequency of occurrence, the number of times between, say, 1 and capital N, when the digit sequence xn plus 1, xn plus k minus 1 matches this digit sequence d that you picked. And we look at the proportion of such digit sequences among the first capital N natural numbers, and we take the limit as n goes to infinity, and we want this limit to exist, number one, and not depend on which digit sequence you chose. So you tell me, what should this limit be? Exactly, thank you. So it has to be 1 over b to the k. Now we are going to say that x is Can you still see here? Okay. X is absolutely normal if X is B normal for all B, and we are going to say that X is absolutely non-normal if it is not B normal for any B. All right. So first things first, every time there is a definition, there has to be a very natural follow-up question. And what is that question? Yes. Are there any such? Because if there isn't, then it's not worth studying very much, is it? So let's talk about some examples. And non-examples. Anything that comes to mind, things that you might want to throw out as you numbers that you know which might fall in one of these categories? Irrational numbers are? That's right, exactly. So very good, thank you. So Q, every rational number is absolutely non-normal. Why? Because rational numbers are characterized by either a finite expansion or a recurring expansion in any base, and therefore it has to prevent nonarity. Okay. Now, you can try to create normal numbers in certain bases, but okay, so let me sort of start with an old result. So this is actually known as Champernoun's constant. And what is it? Well, it's actually the concatenation of all the natural numbers um, in a decimal expansion. So it's 1, 2, 3, 4, all the way up to 9, then 10, 11, 12, you get the drift. So this is a number created by Champernoun. And similarly, there is a variant of this due to Copeland and Erdős. And there, this is the concatenation of all the primes, 2, 3, 5, 7, 11, 13, and so on. And they have managed to show that these numbers are 10 now. It is not known whether there is any other base in which these numbers are normal or not. Okay. These are somewhat artificially constructed. However, what makes the study of normal numbers worthwhile is a very, very old result of Emile Borel from 1909, where he shows that Lebesgue almost every x is absolutely normal. Okay? So essentially, normal numbers are thick on the entire real line. So there are many, which might make the next statement that I'm about to make somewhat ridiculous sounding, but I'm good, it's true. Not a single explicit, absolutely normal number is known. So there is no explicit example of an absolutely normal number? Currently, no. Okay. In particular, we don't know whether the household irrationals like square root 2, pi, e, Euler's constant, gamma, we don't know if these are, it's believed, but a huge open problem with really nothing to grab onto, whether these are absolutely normal or not. Let me be clear. Um, a lot of work, as you might guess, has gone into this because normal numbers are essentially should be thought of as the outcome of a perfect random process on the real line. So it has implications in theoretical computer science. So there is a lot of interest in producing algorithms for generating absolutely normal numbers. It originally goes back to Turing. There has been more recent work by Ted Slaman, Veronica Becker, but these are algorithms. These are not explicit examples. Okay. Anyway, a colleague of mine once described this scenario as saying that, well, I can understand if you can't find the needle in the haystack, but if you can't find the hay in the haystack, then that's just silly. This is exactly what it is. It is a hay in the haystack, but nobody seems to be able to find one. Is that due to Victor said? Okay, thank you. I did not know that, but okay. So, what's our focus for? So today we are going to talk about um, sets of numbers with limited normality. What does that mean? That means these will be numbers which are normal in some bases, but not normal in others. Okay, so let's take a look at, let's set this up. So we're going to take two subsets, B and B prime. These are subsets of bases, could be empty, we don't know. And we're going to denote by script n B, B prime, the set of x's in 0, 1 such that x is B normal for all B in script B, and x is not B prime normal for any B prime. Now, obviously, we want to know if such a thing makes sense, and there has to be some trivialities that we have to get rid of. For example, if B and B prime have non-empty intersections, then obviously this is empty. So those sorts of things. And I need to tell you about this important notion in this business before I can dig deep into the structure of this set. So this is called multiplicative independence. So let me, this plays a role in many problems in geometric measure theory, dynamical systems, number theory. So this is worth visiting. Multiplicative independence. So what exactly does this mean? We are going to say that two integers, r and s, are multiplicatively dependent, and we are going to denote this by r wiggle x, if one can find positive integers m and n such that r to the m is equal to x to the n, which is really the same as saying that log r over log s is rational. Okay? Otherwise, they are said to be multiplicatively independent, and we say with okay. This turns out to be, as in many other problems, this plays a crucial role in this in the set normal numbers with certain bases. And let me sort of cite a few results in this direction. An old result of Schmidt I think this dates back to 1960s, says that a number x is, suppose that r and are multiplicatively dependent, then a number x is R normal if and only if x is S normal. Okay? Which means now we have a little bit more to say that if we want this to be non-empty, then every element in script B better be multiplicatively independent of every element in script B prime, otherwise it would give this to be an empty set. Okay. Now, just because it's non-empty doesn't mean that it has to be very large. How large is it? That's the next question. So let me mention a result and then I'll stop for a breather and ask you questions. All right, so this is a result due to Andrew Pauling Schmidt himself, actually, as a follow-up to his result. This particular result shows that under the usual hypothesis, this is an uncountable set. Pollington took it further. This is, I think, around the 1980s, maybe 82. Says that if B and B prime are multiplicatively independent, which means every pair is multiplicatively independent, then the Hausdorff dimension of NBB prime is equal to 1. In other words, these are of course Lebesgue null sets, and if script B prime is non-empty, but they are about as large as it's possible to be on the real line. Questions? Yes. Script B? Script B and B prime can be finite or infinite, no restrictions at all. If you want, you can think of, let's say, B as the odds and B prime as the evens. Okay. So, so these are large sets in dimension, which is one measure of size. So the question, one question that we were interested in, remember I sort of talked by saying that I'm always interested in these patterns of randomness in deterministic structures. Well, these are large sets, but how rich are they in arithmetic structure? So large in dimension, what can one say? So now I understand that the word arithmetic structure is English, it's not really math, and how you describe arithmetic structure is all in the eye of the beholder. So let me at least talk about a working definition. And this definition comes from, has its roots in very classical harmonic analysis, Fourier analysis. So, and this is one of many measures of arithmetic structure. So these are called sets of uniqueness. So what exactly, you'll see this is another notion of size, not exactly the same as Hausdorff dimension. What is the set of uniqueness? We are going to that a set E of the unit torus is a set of uniqueness if the following is true. Whenever you look at a complex trigonometric series, a n e to the power of 2 pi I n x, n in z, if this vanishes for every x in the complement of E, then that forces the series to be trivial. Okay. All right. So I know this is kind of a weird looking definition, but maybe it's a good idea to sort of stop for a moment and see what it's really trying to say. Okay. So suppose that E is a really, really small set, like say just a single point. Okay. Then if you look at the complement of E, then it has essentially everything. And therefore, the vanishing of this complex series forces an to be 0. Okay. Same for E consisting of finitely many points. So, a smaller E is, the larger its complement is, and the more constraints you have on the coefficients if such an equation has to be 0. Think of it as an uncountable system of linear equations. Okay, so the more constraints you have, the less chance of an being non-trivial, and therefore it forces this. However, if E is large, then it is possible that the complement of E has enough arithmetic properties in it so that such an equality, this could actually have a non-trivial solution. Did I make this clear? So this is one of many ways of determining arithmetic structure. Okay. Now, otherwise, if not, E is called a set of multiplicity. So the question, so this sets of uniqueness and multiplicity have a very, very long history. And an old question of Kahan and Sullivan around 1964 asks, is NBB prime of uniqueness or of multiplicity? In other words, it passes dimension test. Does it pass the multiplicity test? Okay. No, see, this is exactly as it's numerically. Think of, so you fix an x, then this is a numerical series. No absolute convergence, no norm convergence, nothing at all. It is exactly as written. Think of series of complex numbers. And you know, it converges if its partial sums have a limit. That's exactly what this means. All right. Now, um, they were, Kahan and Sapem had a wealth of literature leading up to this question. And they actually phrased this question not as I have done it, rather from something else that they were discussing, which is to do with Rachman measures. So I'm going to say this, restate their question again in the form that they stated it as. And this is where the connection between Fourier analysis and geometric measure theory becomes even more explicit. So I'm going to call this Kahan and Salem's question 1. And here's their question 2. Does there exist a probability measure mu such that um, almost every x, mu almost every x, belongs to NBB prime? So it's essentially supported on NBB prime. And the Fourier coefficients of mu n go to 0 as n goes to infinity. So what do I mean by mu hat? This is, of course, the nth Fourier coefficient. Okay. So smallness of Fourier coefficients is one marker of randomness, and measures which have this property are called Rachman measures. So Kahan and Salem's rephrased question is that does NBB prime support a Rachman measure? And if they did it in this way is based on earlier work. It was known that a yes to question 2 implies no to, well, implies, when I say no, I should specify, implies that NBB prime not of unique multiplicity. Okay. All right. So at least then now I'm in a position to say a little bit about literature. The first real progress in this direction is due to Russell-Arons, and I think 1986. He studied the case where B prime was the single base 2 and B was undetermined. He showed that N2 supports the Rachman measure and is multiplicity. Okay. Last year, yes, yes, yes. Yes, yes. So I think I'm saying this. Okay, let me say. I think I said this right. Let me look at this again. So if there is no Rachman measure, but if there is a pseudo measure, the Piatetsky-Shapiro would say that it's a set of uniqueness. If there is no, if I think it's a yes question 2. So does there exist yes to question 2 implies no to question one, namely that this is not a set of uniqueness. In other words, it's a set of multiplicity. I think I had this the right way. Did I say this right? So the Pianetsky-Shapiro example says that a set of uniqueness is equivalent to the non-existence of a pseudo measure whose Fourier coefficient goes to 0. Therefore, if there exists a metric with the Rathmann property, that implies this is a multiplicity. Did I say this right? Okay. All right. Okay. So this is Leon's that set of multiplicity. So the result that last year I proved with Junqiang Zhang. So maybe I should his name fully. Was to give a complete answer to this question. Which is to say that NBB prime is a set of multiplicity if and only if, whenever it's non-empty, namely whenever they're multiplicatively independent. Okay. All right. So I'm going to take a stop, and see if you have any questions so far. All right. You can still continue thinking while I raise the other board. So in the time that I have left, my goal is to try and tell you, maybe I can't do justice to the entire proof, but there are some aspects proof that I wanted to highlight and maybe tell you as the main takeaway message for today. And that's my goal for the rest of this talk. So I'll come back to the proof of this in a moment. And just to give you an idea how it goes, what we are going to try and show is that whenever B and B prime are multiplicatively independent, I'll tell you how we constructed a Rathmann measure with this property. So I'll tell you that in a moment. But I think I better give you the main message first. So this is not a new concept. This is certainly not our concept, but the manifestation of this is probably what is of interest. So the way I'm going to first look at sort of a toy problem. So let's say we have an S, two bases, okay? Okay. And let's say O is any integer. I'm going to take a look at this set rho times r to the m, and I will look at all possible choices of m going from 0 to s to the k. And I want to study this mod s to the k. Okay. My question is, how does this of residues behave. So let me sort of repeat this question again, because in some way this is kind of the heart of the problem. You have two distinct bases, R and S. I am looking at rho times R to the M, but I am expressing it in base S. So I'm taking an integer in, think of it, which I understand in base R, but I am restructuring it, the same integer, in base S. And how does this work? Okay. So let's work out a silly example. But it will help set the stage. So let's say for the moment R is 2, S is 4. Just checking, linearly dependent, multiplicatively dependent or independent? Dependent. Okay. All right. These are dependent. Okay. So now let's take a look at rho times 2 to the m, okay, mod 4 to the k. Okay. And we are going to look at, say, 0 less than m, less than 4 to the k. Now, any thoughts? How do these residues behave as m starts marching from 0 and goes all the way to 4 to the k? How do you see these numbers changing? What happens, let's say, after m exceeds 2k? That's right. So all of these become 0 for m larger than or equal to 2k. So out of the 4 to the k many possible choices of m, at most 2k minus 1 many have the potential to be anything other than 0. Okay? So these residues are heavily biased towards 0. And now, with this silly example in mind, can you guess what the result is going to be? This was the case when we chose R to be 2 and S to be 4. So, and for that, this kind of heavy bias towards one particular residue. So, if we had to have a really, really interesting randomness result, what would that look like, do you think? Yes, this is a question definitely for the students, not the experts. So you all don't you dare try to answer this. Right. Exactly. So let's say if what if R is 5 and S is 27, and we ran this example again, what would you expect the residues to be? Yeah. No, but I think you're right. You're on the right track. It should be uniform, but uniform where? Yes. Mhm. Okay, so you would take a look at, let's say, rho 5 to the m, and you would look at it mod 27 to the k, And you would run this for 0 between m and 27 to the k, right? So how many possible choices of mod 27 to the k are there? How many residues are there? 27 to the k. And the whole point of this is that such a phenomenon cannot happen if R and S are linearly dependent, in which case these numbers are roughly evenly distributed um, among residues mod 27. You see? So this is what I meant by a randomness inherent in a discrete structure. The actual full result is complicated, but I'm going to give you an example. So this is a result of Schmidt, special case. All right, so I'll write it down in the special case where R is odd and S is 2. Okay. So what we want to do is take any R integer row as row sub 2 and row times row sub 2 prime. Row sub 2 is the power of 2. So it's the highest power of 2 that row will admit, and 2 does not divide row 2. Okay, so I want to now write down what Schmidt's result looks like in this context. So then, for every k larger than or equal to 1, and for every sigma, the possible residue class, which is okay, the of number of m's such that rho 2 to the m mod r to the m mod 2 to the k is sigma. This number is bounded above by something that is, they, as I said, they are going to be roughly the same, and it's a constant that depends only on r times rho. So, for example, if rho was not divisible by 2, this will be bounded above by a fixed constant. And therefore, examples such as these would be ruled out. So if there is one perhaps message that you can take away from this lecture, it's this randomness behavior. And how to use it is, of course, another, which I'm not going to get into too deeply today. But the fact that such a result is there helps us a lot when proving normality or non-normality. Let me again take a break and see if you have any questions about this statement. All right, so how am I doing on time? 6 minutes, okay. 11, oh, I have 11 minutes, okay. Oh, wow, okay. Okay, great. So at least I got the main thing out of the way. I do want to say a little bit more about how I, in the proof itself, I cannot, in our proof, things like this are used to estimate exponential sums, but that's not what I wanted to get into today. I wanted to tell you about this construction of a measure, this which has the Rachman property and is supported in the set of in the set NBB. Okay, so that's probably where we'll have time. So this is the proof idea. So remember, what are we? Yes, please, of course. Yes, yes, correct. Thank you. Yes, that's it. Okay. So remember what this mu is supposed to do. This mu, we want mu almost every x to belong to NBB prime, which means, among many other things, that this has to be non-normal in base B, in base B prime in space B. Okay. Now, how do you create a measure which tries to avoid being normal? Because, as you know, Borel's result says numbers are always trying to become absolutely normal, right? So how do you kind of discourage um, uh, the normality? So maybe that's what maybe we'll have time for today. So let's just talk about a two-step building block which we iterate many times in our construction. So so you should think of it as an elementary operation um, that discourages, whatever that means, we will see in a moment, normality in a certain base. So let's say base S. Okay. So this operation, what it will do is it will take a set density pair and it's going to output another set density pair. So what is E0? E0 is a set which is actually a union of intervals, and phi 0 is a probability density function on E0. Okay. Now I'll try to explain to you what one can do so that when I run my machinery through this and I get back E1 and phi 1, this is a little, it's not going to do it all in one go, but it's a little bit less likely to attain normality in basis. Okay, that's my goal. So let's take a look at E0. So E0 is a set of intervals. So we have E0 is the union of a certain class of intervals, which I'm going to call I0. And the length of each interval I in I0 is some fixed constant, let's say 1 over t. So this is an I, its length is 1 over t. Yes. Oh, I have 5 minutes. Okay, thank you. Um, so what we do now is at the next step, we are going to, from this t above on which I have very little control, I have to somehow get to this base s. And I don't know whether this s is smaller than t, larger than t, I don't know. So to first try to get to an s to the power of a, which is larger than t. And by the way, I haven't told you what phi 0 is. So phi 0 is like a density function which gives a certain weight, wi, to every interval in I0. So think of this. This interval has been given a weight, Wi, and the sum of the Wi's is 1, so that it's a probability density. Okay. So the next thing that I do is I'm going to sort of divvy up this as a first step into sub-intervals of length s to the power of minus a. And s to the power of minus a is less than 1 over t. And at the first step, it doesn't look like I'm doing much. In fact, I'm not. All I'm doing is I'm going to take one of these, throw away the endpoints if they're a little bit, because you see t and s need not be powers of each other. So there may be some little throwaway pieces. But at the first stage, what we do is we take each one of these s to the minus a many intervals and distribute the weight Wi equally among these pieces. So equally distribute Wi among the children. Okay. So this part is not terribly interesting, but it's important for reasons I can describe later. But what's the next step? The second step is that let's take one of these intervals, s to the power of minus a. Okay, and now I am going to decompose it into smaller intervals f to the power of minus b. If we wanted normality, every single one of these children should be getting equal weight. But I don't want that. I want non-normality in basis. Therefore, here, the way I'm trying to force the bias is, let's say I pick some interval here, which is my preferred interval. You can pick your preferred interval in whichever way you want. What I'm going to do is I am going to look at the weight that this interval has, whatever that weight may be. Let's call this weight W star. I'm going to give 1 minus epsilon W star divided by s to the b weight on every single one of them. So every single children receives this much weight, right? But this is b minus a. But this one gets extra. So this one gets a weight epsilon plus 1 minus epsilon W star. Do you see? So what we have done is this particular interval, which corresponds, particular example, to the digit 0, it got extra preferential treatment. So therefore, it sort of is one nudge towards non-normality in base S. Of course, it's still not there because it's still a density, but I have to keep doing it again and again and again until I get to the point where I show that in the end, what I get is non-normal in base S. Okay. So I think it's a good place to stop, because showing non-normal in base S doesn't necessarily mean normality in all the other bases that are multiplicatively independent of S. That's another can of worms, but that's where all this randomness inherent in deterministic structures. I think it's a good place to stop. Thank you for listening.
Yeah, thank you. Are there any questions?
You can comment on how, when you do this construction, how do you control the Fourier coefficients to get the Y-1 measure?
Yeah.
Iteration somehow increases the Fourier. Can you say something about the idea?
Let me try. Yes, let me try to say hopefully something sensible. Okay. This is something that at least the way I have described it in the most general setting This is not a product structure. If you think of your standard Cantor set, when things fit exactly within each other, the Fourier coefficient has a product structure. That is not the case here, but let's pretend for the moment, which is the case, and we don't have to pretend this. In the example of Russell, in the measure constructed by Russellian, this is the actually happens. It's an infinite product, and this product has a particular expression, and then there is a function here. So I'm going to call it n. Okay. So that is the product structure, and these epsilon L's are these different biases, and they have to sum up to infinity. You can think of these as 1 over L. So when I am plotting the Fourier coefficients, and I want to make sure that this is a Rachman measure, I have to show that this goes to 0, correct? Now, the way this can go to 0, when you look at this product, with both of these, when you have to compare the relative sizes of these two things. Now, in some cases, if the epsilon L, if like all of these are zeros, then epsilon L, the product of them will be small, which is fine. But something that's really important for us is to understand that this is the trigonometric function. It's a trigonometric function which has n times 2 to the power of minus k built into it. The important thing and here is, when does this take large values and when does this take small values? Something that was curious for us, and I thought it was very big in Leonce's work, is that when you look, the size of this depends on the digit expansion of n in base 2. And the more times when you express this, let's say as ni 2 to the I, this ni is either 0 or 1, the number of flips, the number of times in the digit sequence 0 and 1 occur, in other words, the less number of straight runs there are, a straight block of zeros or a straight block of ones, as long as there are many flips, you have a good estimate. That's the important thing. Now, is it possible for digits to have straight blocks? Of course. But can there be very many? Of course not. And that's what kind of saves us. So that's for the Rachman property. Another just follow up is, once one has the Rachman property, we thought foolishly that perhaps showing the Rachman property would also give us some help in proving the normality. That again, that did not turn out to be the case, because even though the Rachman property, the decay of these Fourier coefficients turned out to be true, the decay was too weak to actually prove normality by simple means. These Fourier coefficients, if you draw a picture, this picture is a good one to keep in mind. So let's say this is n, and this is absolute value of mu n hat. So these mu n, they obviously go down to 0. But the important thing is, when you look at the bound get, so let's say that this is the maximum value. For large chunks, mu hat of n is actually far, far smaller than what the largest possible. Does it attain some? Of course. But for the big portions of time, it's actually exponentially small. And that's what helps us with the normality. That's that structure, that even though this, it may look like this is like, let's say, 1 over log n, let's say. Okay, and 1 over log n can show up here and can actually be attained for some n's, but for the vast majority of the n's, it's actually harmless.
Any other small questions? Okay, if not, let's thank the speaker.